Hello students, today we are going to talk about theories of coordination complexes. Learning objectives are bonding situation in coordination compounds as explained by valence bond theory VBT. Valence bond theory of coordination compounds, basic postulates and applications. Okay, we are now moving below. First of all, we have valence bond theory, which is also known as VBT, firstly developed by Pauling, deals with electronic structure of central metal atom in its ground state, kind of bonding geometry and magnetic properties of complex. To overcome certain limitations, this theory was modified by Huygens. Now we are moving valence bond theory. The modified theory is based on following assumptions. The central metal atom or ion make available a number of empty sp and d orbitals equal to its coordination number. The vacant orbitals hybridize to form hybrid orbitals which are equivalent in energy and have definite geometry. The ligands have at least one sigma orbital containing lone pair of electrons. Now we are moving toward assumption number 4, the hybridized vacant orbitals of metal atom with the field sigma orbitals containing lone pair of electrons of ligands to form ligand to metal bond known as coordinate bond. The coordinate bond thus formed shows the characteristics of both the overlapping orbitals. The non-bonding electrons, valence electrons of central metal atom are then rearranged in unhybridized orbitals of metals according to Aufbau principle and Hund's rule. The octahedral complexes are formed by mixing of 1s3p and 2d orbitals. The 2d metal orbitals which are involved in hybridization must be dx2 minus y2 and dz square. These are e.g. two orbitals which are involved in hybridization. On the basis of VBT, octahedral complexes are of two types. Inner orbital complexes involves inner d while outer orbitals complexes involve outer d. These contain usually 3d and these usually contain 4d. Okay, now we have inner orbital complexes involve hybridization of n-1d square ns-np3 orbitals. Consider the example of CONH3 6 plus 3 to explain the bonding according to BBT in such complexes. In this complex line, cobalt is present in plus 3 oxidation state. In this complex sign, cobalt is present in plus 3 oxidation state. The electron configuration is 3d6, 4s0, 4p0. Okay, 3 is n minus 1d orbitals. CO3 positive ion, its configuration will be as following. In order to accommodate 6 electron pair donated by 6 ammonia ligands, 6 vacant orbitals namely Eg2 and 1s and 3p orbitals are available. As we have talked that Eg square orbitals will be involved in hybridization. This can be done by transferring 2 electrons, one from dx square minus y square and dz square and to dyz and dzx. 6 electrons of cobalt 3 positive get buried up in dxy, dyz and dzx. Since ammonia is a strong field ligand, it will cause pairing because splitting will be very high. This leaves the 3dx square minus y square and 3dz, 4s and all the 4p orbitals vacant which are mixed to form 6 equivalent d2sp3 hybridized orbital directed toward the 6 corners of regular. Okay, this type of complex is known as inner orbital complexes since inner orbitals n minus 1d are involved. So after hybridization and before hybridization, you can see the configurations. The octahedral geometry of CONH3 6 plus 3 complex sign is shown in this figure. Since all the electrons are paired in CONH3 6 plus 3 complex sign, so it is low spin because all the electrons are paired. As you can see here, you can see CO3 positive after hybridization, all the electrons are paired. Outer orbital complexes involve outer D. Consider example of COF6 minus 3. F6 is a weak field ligand. Outer complex orbitals are formed by weak field ligands. Physical measurements revealed that these are paramagnetic in characteristics because electrons are unpaired. Ligands are weak field, electrons splitting will be high, and electrons will be unpaired. The one 4s, 3p, 4p and 2 4d orbitals will mix to give 6sp3d square hybridized orbitals which are vacant and can overlap with 6f-1 ions to form cobalt COF6 negative ion. Here you can see the structure. Valence bond theory. Since complexes are called as outer orbital complexes, since outer d orbitals n d are involved, n mean the valence shell orbitals, n minus 1 mean 1 before the valence shell. Here we will talk in next video about the applications of VBT to tetrahedral complexes. Thanks for watching.